I'd like to go over a quick proof for the power rule today. And as a reminder, the power rule says that if we have a function which is our input x raised to a constant n, then the derivative of this function will be the exponent n times x to the power of the exponent minus 1. So for example, if we have a function of x is equal to x to the power of 5, here n is 5, so our derivative would be 5 times x to the power of 1 less than 5, 4. So we can use the limit definition of the derivative to show why this works. So let's do that today. So if our function is our input x raised to the power of a constant n, then our limit expression as h approaches 0 would just be that function, so x plus h to the power of n, let me draw a better h, minus x to the power of n. So we're just swapping in our function, which is raising it to the power of n, and that's what is going up here in the numerator, and it'll still just be over h. Now where do we go from here? Well, we can't expand this out very easily, but we can get away with only doing like a half expansion. You'll see what I mean. Let's say we have x plus h times x plus h times x plus h, and I'll just put dot 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 so that there are a total of n of them. Now let's try expanding this. Our first number is going to be all of the x's multiplied by each other. And how many of them are there going to be? Well, there should just be n of them. If we have n binomials, then when we're doing all those multiplications with the x's, it'll just be x to the n. Here it gets a little bit more complicated, but we're going to do one more term. Let's do the terms where there is one h and the rest are x's. So we're going to take one h from here and multiply it by all the rest of the x's. So it'll look something like this. We have that h from this binomial multiplied by the x here, and the x here, and the x here, and the x here. How many x's will there be total in that term? Well, it shouldn't be a full n because one of them is replaced by an h. So it'll just be one less than however many binomials we have here. It should be x to the n minus 1. Now that was just when we took this 1h, but there should be more of these terms, more similar terms, when we take 1h from, let's say, this one. And now we multiply it by this x, this x, this x, this x, etc. Again, it'll just be 1h that we're taking now from here. And again, it'll be x to the n minus 1. Because we didn't count the x from this binomial, but we counted all the rest of them. Now, how many of these are we going to get, of these terms? H times x to the n minus 1. Well, we're doing one of them for each binomial. We first did it using the h here, then we did it using the h here, then we could do it using the h here, and we could do it once for however many binomials we have, for n binomials. So, putting these together, there should be n of them. Because there should be n instances of us taking one h and multiplying it by the rest of the x's. Okay, so putting this all together, we have x to the n plus n h times x to the n minus 1s. And then after that, it gets crazy. But the good news is, we can kind of get away with just leaving it mostly here. What do I mean by that? You'll see later, but what we have now is a bunch of terms with more than one h in them. Let's say, for example, we were to take these two h's and multiply it by the rest of the x's, and then maybe these two h's and multiply them by the rest of the x's. Or maybe we'd take three h's, multiply them by the rest of the x's. These are going to be a whole bunch of terms with h's to the power of more than 2. So I'll say h to the power of some unknown number, a, where a is greater than or equal to 2. That's just how I'll write it. Let's put this back into our limit definition for the derivative. This is what our limit expression will now look like. We have our x to the n plus nh x to the n minus 1 plus a whole bunch of terms where we have h raised to a larger power, and then still our minus x to the n all over h. And notice these two can cancel out quite nicely. And also notice now that all of these terms in the numerator should have h's in them. And that'll be quite nice because it'll allow us to cancel this out. Let's try factoring out an h. So the limit as h approaches 0 of h times n x to the n minus 1, and now that h is in front, plus these terms now, if before they all had a power of 2 or more, they should now just have a power of 1 or more. So terms with h to the b, let's say, where b is greater than or equal to 1. Boom. Now we can get rid of those h's and just substitute in our limit because we got rid of the denominator. If we do that, all of these terms where we have an h in them, doesn't matter if it's just an h to the power of 1, it could be an h squared, an h cubed, whatever they are, they're going to equal 0. When we plug that h is approaching 0 in, all of these terms are going to go away. And that's what I meant when I said we don't really have to worry about this very much because they're gone when we plug in h is approaching 0 into these terms. And so this all boils down to just this here. N times x to the n minus 1. And that is our power rule. So hopefully you appreciated this explanation for the power rule and you found it interesting or useful. And let me know if you have any questions.